You'd ask about one of the homework problems, S2.4. So VZ of T is equal to AB e to the minus gamma Z cosine omega 0 T. And then says use equation 3.3 from the text. So that equation is minus partial with respect to Z of VZT is equal to R prime IZT plus L prime partial of T. And there can be a form to assume for I. Yeah. I see the confusion. There's a mistake in the problem statement. It should have said VZ of T is equal to this, and IZ of T is actually has a different amplitude. Same attenuation factor. And then same frequency, but a different phase. So if that was the problem, because in the actual problem statement, which I just now noticed, it has VZ of T for both of those. Okay, so was that the issue?
No.
Okay. Well, so proceeding for the first one, the derivative of this with respect to Z would be minus gamma. Take the derivative of this with respect to Z. It's minus gamma AV e to the minus gamma Z cosine of omega 0 T. And the RI term is just going to be R times that. But then the partial with respect to T of I would be take the derivative of cosine, you get sine, and then pull out the omega 0. It's actually minus sine, right? AI e to the minus gamma Z sine omega 0 T plus phi. If you write this, actually, we're going to now plug all this into that equation. But the other thing we want to do is actually, we typically use our cosine as our reference, especially when we go into the phasors. And so what we want to do here is write the sine, represent the sine as a cosine. So the sine is actually just the cosine shifted to the right, minus pi over 2. Okay, so we'll do that. AI e to the minus gamma Z cosine omega 0 T plus phi, and then minus pi over T. Now I get rid of the minus sign here. We don't actually have to do that, but I can get rid of the minus sign here by adding or subtracting pi, shifting it at 180 degrees or pi radians, and you would typically, I'm going to add pi so that, well, I don't really know what, to keep the phase angle kind of is in the range between minus pi and plus pi. So now plugging into this this equation, so we've got the derivative, but it's a negative of that, negative gamma AV e to the minus gamma Z cosine omega 0 T is equal, on the right-hand side, I'll have R prime AI e to the minus gamma Z cosine of omega 0 T plus phi, and then plus L prime times this omega 0 AI e to the minus gamma Z cosine of omega 0 t plus 5 plus pi over 2. Okay. So the e to the minus gamma t gamma z term actually cancels out. That's everywhere. And then here I've got a sum of cosines at the same frequency. If you remember the trick to avoid, since they're at the same frequency, I can just use phasors to add them together. Okay. And so the phasor representation of this is r prime ai e to the j phi. It's just the phase angle. Remember, we drop out the omega 0 t. That's the phase angle corresponding to this. This is omega 0 L prime ai e to the j phi plus pi over 2. Okay. And then over here, I would have gamma AB e to the j 0, which is 1. Okay. So I'm almost there. We're asked to solve for AI e to the j phi, right? So I can actually, I'm almost there. E to the j phi plus pi over 2, I can write as e to the j phi, e to the j pi over 2, right? Product, we add the exponents. But what's e to the j pi over 2? Remember, that's on the unit circle. It's at an angle of pi over 2. I could express that a little more simply in rectangular form as what? Here's 0 degrees. Here's pi over 2. Pi, minus pi over 2. So pi over 2 is right on the imaginary axis, right? And it's on the unit circle, distance 1 away. So another way to write that is it's just j. This is just j. So j omega 0 L prime ai e to the j phi gamma ab. And then now I think I have the final result. I can factor out the ai e to the j phi term out of the right-hand side, and I'll have gamma r prime plus j omega 0 L prime times av. And I think that's what you're asked to prove in the homework. So, and so I guess watch out for that. Anytime you've got a sinusoid that's the same frequency, you can add them without using all the trig identities. And it's usually a lot easier to actually use phasors. Okay. So we started last time working with the telegrapher's equations and we modeled a section of transmission line like this. R prime delta Z, L prime delta Z, G prime delta Z, C prime delta Z. And then we're assuming here that the transmission line is a straight line laid out on the delta Z axis. And this is a piece of that transmission line that we're calling delta Z long. And we want to come up with a relationship between actually the voltage along the line. So this is Vz of t, whatever z is, whatever distance that is along the line. This is Vz plus delta z of t. Okay. So again, on the transmission line at the high frequencies, it's unlike at lower frequencies where a wire is a node and the voltage is the same everywhere on that wire relative to ground. The current's the same everywhere on that wire. On a transmission line, that's no longer true. At high frequencies, it takes time for these voltages and currents to propagate down the wire, to move down the wire. You have that same issue in free space. Okay. It takes, radio waves in free space travel at the speed of light. We'll see that radio waves on our transmission line actually travel a little bit slower than the speed of light. But it still at the speed of light, it takes time for radio waves to propagate from one position to another in space. So this is the notation we use for the voltage. And then this was our current notation. In the phasor form, so if we assume that the voltages and currents are sinusoidal, if they're driven by a sinusoidal source, then the telegrapher equations that we had and we'll call this equation 1, where V, this is a tilde of Z, and I tilde Z, this is the notation he uses in the book. For the phasor, it's a function of distance now, so it's not just a constant. It is a complex value. It has magnitude and phase, but those can now be functions of distance along the wire. So that's the one equation, and then the second equation was similar in form. C prime V of Z, where we can recover the time domain expression from the phasors mathematically. That's the real part of, we take the phasor and multiply it by j omega t to get back to the time domain expression for voltage. Okay. Or equivalently, we can go from we can get the phasor from a time domain expression. This is, again, if this is a cosine, this is that complex number that involves the amplitude and the phase. But this is now a function of distance. And then similarly, Iz of t is recovered the same way. It's our current phasor times e to the j omega t. So if you differentiate 1 again with respect to z, I'm going to skip a few steps of algebra. He has this proof in the book. But if you differentiate equation 1 with respect to z, you'll get a second derivative with respect to z here for v of z. And on the right-hand side of equation 1, you'll get this term times the partial derivative of I with respect to z. Well, we've got an expression for the partial derivative of I with respect to z in equation 2. So if I now make this substitution back into the derivative of equation 1, I'll have a single equation just involving my voltage phasor. Okay. So doing that, we get partial with respect to z squared of my voltage phasor minus gamma squared v of z is equal to 0, where when I make this substitution, I'll have the product of these two terms. Okay, I'll have r plus j omega L times the derivative of this, so that'll give me the g plus j omega c prime. So gamma squared in this equation is r prime plus j omega L prime g prime plus j omega c prime. So you can see in general, this gamma squared is complex, and gamma then of course would be the square root of that, r prime plus j omega L prime g prime plus j omega c prime. You can also see in general this, it's a complex propagation constant. In general, gamma is going to be a complex value that's a function of frequency. Now this is a wave equation. Okay, we looked at a form of this back in chapter 1. Okay. There it was actually acoustic pressure. We talked about sound waves, but it was acoustic pressure. And then this term was actually 1 over the wave velocity. Okay. So, but this is a wave equation. But gamma is what's called the propagation constant. You could do something similar with the second equation, take the derivative of it with respect to z. On the right-hand side, we'll get partial of v with respect to z, take equation 1, plug it in. You'll get a wave equation for the I phasor. V minus gamma squared I tilde z. Actually, it's the same wave equation, same propagation constant. So the solution forms for the voltage and current will have to be the same, except for they can differ by a complex constant. You know, I can multiply either one of these by a complex constant, and it would still be a solution to the equation. So my I and V phasors just differ by a multiplicative complex constant. But that means they can have different amplitudes. Remember, they're phasors. So back in the time domain, they correspond to sine waves. They'll have different amplitudes. They can have different phase angles. We'll also see, because gamma here is typically complex, that in the general case, they're attenuated sine waves. The solutions, well, the solution to the top equation, let's call it equation 3 here, and the one for the current 4. But it has this form, e to the minus gamma z. This will actually represent a wave propagating in the positive z direction. We'll see that when we get back into the time domain. But in the general form of the solution, there can also be another wave that's propagating in the opposite direction. Now, typically, and you'll see this, and we're kind of in the derivation of getting some results, and we'll do some numerical calculations in just a bit here for real coax. But typically, the way you get this backwards traveling wave, you know, our problem here is we've got this transmission line, our source is at z equals 0, and our load is at the other end of the transmission line. Okay, so where does this backward wave come from? Well, on a transmission line, you can actually get a reflection from the load. and you can get a wave then that's traveling back toward the source. Now, if the transmission line is terminated properly, you don't get that reflection. So it's like an echo, something that's coming back from a wall for an acoustic pressure waveform that's actually traveling back. Now with an echo, that's generally a pulse that transmits there, hits the wall and comes back. Here we're talking about sinusoids. So at my source, I've got this tone that I'm generating at a certain frequency. It propagates to the wall and comes back. But now I've got both of those waveforms going all the time. So there's interference between those two. So, and we'll talk a lot about that. But this is the portion that's propagating down the transmission line. This is the reflected portion. And we have the same for our current phaser. We have a portion that's propagating down the line and a reflected portion. So we'll call these 5 and 6. Where V0 plus, V0 minus, I0 plus, I0 minus are all complex constants. Characteristic impedance. Now I mentioned that our I and V waveforms are the same. 3 and 4 are identical equations. Yes?
For equation 6, is that on the right side, on the reflected portion, then
it should be positive. Thank you. Mentioned that the wave equations, equation 3 and 4 are identical, so the solutions are the same except for a constant. So we're actually going to define this constant to actually be the ratio of V to I. Now the ratio of V to I, we've worked with that back in circuits 1, that's called resistance, right? Or when we're working with phasors, the ratio of V to I is called impedance. So we have that here on our transmission lines. There's a constant ratio between the V phasor and I phasor on our line, okay, for the waves propagating in each of the directions. That's called the characteristic impedance of the line. So if we substitute 5 into 1, and solve for I, we get, so take this equation for V and go all the way over here. Going to take the derivative of it with respect to Z, plug it into here. And then with that same form, with this form for I, we get that I0 plus is equal to gamma over R prime plus J omega L prime V0 plus, and I0 minus is the negative of that, R prime plus J omega L prime V0 minus. But we have the same ratio of this, our propagation constant divided by R prime plus J omega L prime. So since that appears, we're going to give that a new name. That is, actually, we want the ratio of V to I as an impedance. So the impedance would actually be the reciprocal of this, R prime plus J omega L prime over gamma. But if you take our expression for gamma here, it's the square root of R plus J omega L prime times G prime plus J omega C. So we've got R prime plus J omega L prime divided by the square root of R prime plus J omega L prime. So the characteristic impedance becomes j omega c prime. It depends on, you know, all four of the parameters of our transmission line. The resistance, the inductance, again, these are all per unit length. The intrinsic conductance and the intrinsic capacitance of the line. And remember, these aren't really components in the line. Okay. This is a model for a transmission line at high frequencies. With this definition, we have V0 plus over I0 plus is equal to the characteristic impedance, and V0 minus over I0 minus is equal to minus the characteristic impedance. The minus sign here appears because we've defined our current flowing to the right, and in the reflected wave, the current is actually flowing in the other direction. So that's why the minus sign appears. Voltage doesn't, you know, voltage doesn't have a direction, it has a polarity, and we've defined the polarity to be the same here for both the forward propagating wave and the reflected wave. So Z0 is the characteristic impedance. So you can look up, Google this. There may be a table in the book. You can, for different types of coax, for different types of strip line, depending on the dimensions, you can look up what these parameters are for any transmission line. Now notice the characteristic impedance is typically a function of frequency. In a lot of cases, though, especially for coax, Z0 is typically real, and so, or approximately real. So we'll see how that comes about with, this is RG59 coaxial cable is a common coaxial cable that's often used for television connections. But it has the parameters. R prime is 0.164 ohms per meter. Okay. So pretty low resistance cable. You know, 100 meters of it, which is a fairly long distance, longer than a football field, would have about 16 ohms of resistance, right? So it's a fairly long length of cable. Would have a relatively small resistance. You know, multiply this times 100 meters to get the 16 ohms. And then the conductance is 200 microsiemens per meter. Now remember, this is the conductance between the outer conductor and the inner conductor. Okay. Ideally, we would want zero conductance between those because that would be an infinite resistance. Right? So the smaller each of these are, the better. Ideally, we would have zero resistance. We would have zero conductance between the two conductors, which would correspond to an infinite resistance. And then the capacitance is 67.7 picofarads per meter, and the inductance is again, ideally, in an ideal coaxial cable, both of these would be zero as well. Because the inductor is, you know, in series, it's opposing our current. So we want the impedance here, J omega L, to be zero. You know, ideally, our coaxial line would be a pair of wires. Okay, so ideally, we'd want both of these to be zero. Okay, so that impedance is zero. Here, the impedance of a capacitor is 1 over J omega C, right? So to get that infinite impedance, 1 over j omega c, we want c to be 0 as well, to have infinite impedance. And ideally, we'd like these two elements to be short circuits. We'd like these two elements to be open circuits so that there's no conductive path between the two wires. And find the characteristic impedance at a frequency of 100 megahertz. And that's actually a little lower than the standard television frequencies, which are up in the 300 megahertz, 400 megahertz, but it's that's an FM radio frequency, right? 100 megahertz is right in the FM band. FM band goes to 88 up to 106 megahertz, I think. So that's actually in the FM band of frequencies. Okay, so omega is 2 pi f, so that would be 200 pi times 10 to the 6. And then to get the characteristic impedance, again, a lot of complex number calculations here, so I hope you know how to use your calculators to do these. But r prime plus j omega L prime, well, this is going to be 0.164. J omega L prime, here 200 pi times 10 to the 6. L prime, that's 370 times 10 to the minus 9, or 0.37 times 10 to the minus 6. So you're going to get the 0.37 times 200 pi. That becomes J 232.5 when you do that calculation. Notice that this term is dominated by the j omega L term at this frequency. Okay, so this term is almost entirely imaginary, or the inductive impedance is much larger than the resistive impedance in this line. And again, this would actually be ohms per meter, okay, because I'm not doing this over a distance of line yet. Notice the Z0 actually has the primed values in it, not the, if you did it over a distance, all of these would be multiplied by the same distance and that would just cancel out. And then similarly, the G prime plus J omega C prime, it becomes 200 plus J 42537 times 10 to the minus 6. So actually it's small compared to the R prime plus J omega L prime term because of the 10 to the minus 6 here. But again, notice that this is also almost entirely imaginary, right? 200 plus J 42,000, on the complex plane. It's going to be a small resistive part, but almost entirely imaginary. The phase angle here is going to be close to 90 for both of these. So plugging in, well, I'll do it 2 steps. You get 5,466 at an angle of 0.2290 degrees. And here I gave this, I'm switching between rectangular and polar form. Could write this in rectangular form. This is almost entirely real though, because the J's cancel out here. This is almost entirely imaginary. This is almost entirely imaginary. The J's cancel. We get something that's at a very small angle relative to the real axis. So this is almost entirely real. Z0, the characteristic impedance, is the square root of this. And that turns out to be 73.93 at an angle of 0.1145 degrees. Okay. Again, almost entirely real because of their very small angle. Close to 90 degrees, that would be almost entirely imaginary. But here it's close to a 0-degree angle, so it's almost entirely real. The characteristic impedance is about 74 ohms. The accepted value for characteristic impedance, and you can Google this, what's the characteristic impedance of RG59 coax? And what you'll find is it's 75 ohms is the generally accepted value. Now, and the 75 ohms is kind of an approximation. Where does, it certainly appears as if the characteristic impedance should be a function of frequency because we've got the omega L in there and the omega C. So it appears that that should be a function of frequency. But if you notice, and this is typical, that our j omega L term is much larger than the R term, and the j omega C term is much larger than the G term. So if we neglect the R and the G, then the j omegas cancel out. And to a good approximation, here Z0 is approximately j omega L prime over j omega C prime, which is just L prime over C prime. In this case, that's 73.93 ohms, close to the 75 ohm accepted value. And so, again, this really depends on the transmission line. This wouldn't be true for a transmission line where the R and G values were large. It's only true, at very high frequencies, or in transmission lines where R is small and G is small. And these are called low loss transmission lines. And we'll look at them in more detail next time. But for low loss transmission lines, this is a pretty good approximation. The characteristic impedance is just L divided by C. We mentioned last time that in transmission lines, there's a certain mode of propagation of the electric and magnetic waves. Okay? They're transverse to each other. So the propagation mode is called the transverse electric magnetic propagation. So this is the dominant mode that exists on coaxial cable, on microstrip. Again, at higher frequencies, we get these other modes of propagation, which are common with waveguide and fiber optics. So we're going to take a look at what's going on here in a little more detail. So going back to our expressions for our phasors. I'm going to call the wave that's propagating down in the positive Z direction, I'm going to call that phasor just V plus. Okay. It includes this e to the minus gamma Z term. And then similarly, we'll call the other one, I know there's a lot of notation you have to absorb here. That's one of the confusing things when working with electromagnetics, is just the overwhelming number of variables that you run into and the notation. And similarly for our current phasor, so this expression we've had previously, but then the very right-hand sides are, We're just simplifying the notation here a little bit. And let's look at just this term initially, simplify things as much as possible. So the voltage that's propagating down the z direction. Now, be careful in the homework. You know, some of the problems I think he has, the coaxial cable is laid out in the x direction or the y direction. Okay. It's still a line. You just substitute x for z in these equations or y for z. We're still dealing with propagation down a line, down in one dimension. Okay. Not general three-dimensional propagation or anything like that, which we'll deal with when we run into propagation in free space. So we said that these are complex numbers. So I'm going to write it in exponential form with a magnitude phase. Yeah.
Is that how it's supposed to be? Just one of those BO, or are they all supposed to still be like BO and IO? Or is that exactly how it's supposed to be?
Are you talking about over here?
Yeah.
This should be, what have I got in my note? Yeah, that O shouldn't be there. Thank you. So, yeah. So each of these are actually complex constants. So that's the other thing. Got to keep track of, you know, what's a real constant, what's a complex constant. So this is a complex constant. And our propagation constant, which is, you know, over here, it's the square root of r prime plus j omega L prime, g prime plus j omega c prime. It is, in general, is certainly going to be complex. In the low loss case, we'll have j omega squared. That would actually come out, and we would just have j omega, and it would be entirely imaginary in the low loss case. But in general, it's complex. And writing it in, you know, whatever it is, rectangular form. And I didn't calculate the propagation constant for the RG59 cable. We could have, right? We took the ratio of those, but I didn't actually take the product of those two terms. Then, since going back into the time domain, the real part of this phasor times e to the j omega t, or the real part of, now making this substitution V0 plus, and then for gamma, here I've got gamma times z. Well, that's going to become minus alpha z plus minus j beta z. So that gives me e to the minus alpha z. And then I'm going to combine all these terms that are multiplied by j. I'll have omega t minus beta z, and then plus psi, the angle of this complex constant. So this is real, so I can pull it out. The exponential term here is real, so I can pull it out. The real part of this, of e to the j theta, by Euler's formula, is just cosine theta. So this becomes just cosine omega t minus beta z plus psi. And this, if you go back and look at what we did in chapter 1 when we talked about acoustic waves, this is a sinusoid that's propagating in the z direction, in the positive z direction. Okay. Now, this e to the minus alpha z term means that the amplitude is being attenuated the farther we go down the line. So if I were to draw this, Let's draw it at time equals 0. And just for convenience, I'm going to say this phase angle is 0. What this would look like is it's a cosine, but with a decreasing amplitude. The amplitude is decreasing due to this presence of this e to the minus alpha z term. Okay, the amplitude is getting smaller with distance. Then ideally, alpha would be 0, and we wouldn't have attenuation as our wave went down our transmission line. Again, the alpha will be 0 for this low loss case, and we'll look at that more next time, where both r prime and g prime are 0. Alpha will be 0, and we won't have attenuation. We won't have a decreasing amplitude. The distance between peaks or zero crossings, of course, is lambda. And if you remember, the speed at which at any point on this waveform, it looks like it's moving to the right. Okay, that's the propagation velocity. So alpha is the attenuation constant, and beta is the phase propagation constant. And back from chapter 1, lambda and beta are related. Lambda is equal to 2 pi over beta, and the propagation velocity is omega over b, or lambda over f. Similarly, you can get an equation for the I plus term. It's going to be different. It's V0 divided by the magnitude of the characteristic impedance. And then we'll have a phase angle term of our characteristic impedance. We'll look at that next time. But for our RG59 case, gamma is approximately j omega L prime, j omega C prime. Again, because these two terms are so large compared to the R prime and the G prime terms, or j omega L prime C prime. So again, this implies that alpha is 0, and that goes along with no resistivity, no conductance. Okay, alpha is 0, there's no attenuation in this line with this approximation. And in real life, we know there is some. I talked about, over 100 meters, it's got 16 ohms of resistance, but it's a pretty good approximation. This is true. So this implies actually alpha is equal to 0, and beta is omega L prime C prime. So that phase propagation constant actually depends on the frequency. Okay. I'll give you one last result. The propagation speed in this RG59 is omega over beta. Okay, so the omegas here actually cancel out. It's 1 over the square root of L prime C prime. That turns out to be pretty close to 2 times 10 to the 8th meters per second. What's the speed of light? 3 times 10 to the 8th meters per second. So the phase propagation velocity in RG59 is about 2/3 the speed of light. Okay, so our waves here are going to propagate more slowly than they would in free space or in air. And that's due to the inductance and capacitance that are present in our coaxial line. So we'll get to, next time we'll talk about low loss lines and look specifically at coax and be able to do some calculations. I know a lot of theory at this point, but hang in there.